Hello, this is a Chapter 17 review for entropy, free energy, and equilibrium. For the chapter outline, we'll be reviewing 17.1, the three laws of thermodynamics, 17.2, spontaneous processes, 17.3 being entropy, 17.4, the second law of thermodynamics, and we'll go on to 17.5 for the Gibbs free energy. Then we'll do 17.6 for free energy and chemical equilibrium, and 17.7 thermodynamics in living systems. So we'll go over first the 17.1 section, which is discussing the three laws of thermodynamics. In thermodynamics, there are three known laws together called the three laws of thermodynamics. The first law states that energy cannot be created nor destroyed, but it can be converted from one form to another different form, and this would be considered the first law, but it can also be measured through the change in enthalpy or otherwise the heat that's given off or absorbed by the system, which can be symbolized as delta H. We also have the second law of thermodynamics. The second law explains that the universe's entropy increases in a spontaneous process, and in an equilibrium process it remains unchanged. And the universe is made up in this second law of a system and the surroundings. Thus, the entropy of the universe would be delta S for universe, and for a process it's seen mathematically as the change in entropy for the universe, which will equal the summations of the change in entropy for the system plus the change of entropy for the surroundings. If, for example, the summations add up to a number that's greater than 0, it would be considered a spontaneous process. But if, for example, it was to add up something equal to 0, it would be considered an equilibrium process. The third law of thermodynamics is also considered as a brief extension to the second law, stating that a perfect crystalline substance's entropy is 0 at an absolute temperature of 0. It could be visually seen as here. It would be the increase in temperature would be seen into the crystallines here. Then we could see also that the third law explains how and why chemical processes favor one direction in the reaction, and in a perfect crystalline, the entropy would be 0 at the absolute 0 temperature.
So now we're going to cover section 2 of chapter 17, which is spontaneous processes. So thermodynamics allows for one to predict whether a reaction will occur or not, depending on there being a certain temperature, pressure, and concentration. So if the reaction does occur under the given set of conditions, then it is considered to be spontaneous. But if it does not occur under these conditions, then it is non-spontaneous. So a spontaneous reaction will occur in one direction, but it can't take place in the opposite direction. So some everyday examples of a spontaneous reaction would be a waterfall will always run downhill, but it will never go up spontaneously. And iron exposed to water and oxygen can rust, but it will not turn back to iron spontaneously. It will remain as rust. Or in the morning when you dissolve a sugar cube into your coffee, it will not spontaneously go back to its original form. Exothermicity favors the spontaneity of a reaction, but it does not guarantee it. So an example would be the decomposition of mercury to oxide, and it is an endothermic reaction and non-spontaneous at room temperature, but it does become spontaneous when the temperature is raised. And in an endothermic reaction, it can be spontaneous just as an exothermic reaction can be non-spontaneous, but to fully make and support this prediction, you would need the thermodynamic quantity of entropy, or S. So now we move on to section 3, which is entropy. So entropy, or S, is a measure of how dispersed the energy of a system is among the different ways the system is capable of containing energy. So the greater the dispersal, then the greater the entropy will be. Most processes can have a change in entropy. For example, a cup of hot water has a certain entropy due to the dispersal of energy between the various states of energy in the water molecules. Energies associated with translational, rotational, and or vibrational motions of water in the molecules. But if the cup is left alone on the table, the water will lose its heat to the cool surroundings. So the probability of the occurrence of a particular state will depend on the number of ways that the distribution can be achieved. So the entropy of a system is related to the natural log of the number of microstates, or W. So the equation would read S equals K natural log of W, where the K is the Boltzmann constant 1.38 times 10 to the power of negative 23, and the larger the W is, the greater the entropy of the system will be. The entropy change for the process delta S is delta S equals SF minus SI, where SF is the final entropy and SI is the initial entropy. So respectfully, the equation can read delta S equals K natural log WF minus divided by WI, where WF is the number of microstates in the final reaction and WI is the microstates in the initial reaction. Sorry about that. So in a solid, the atoms are confined to a fixed position with a small number of microstates. So when it melts, the atoms are able to occupy more space and more positions because they can move from the lightest points. So it's then assumed that because the number of microstates has increased, then the order to disorder phase or transition can result in an increase in entropy. Vaporization will also lead to an increase in entropy in a reaction, so the increase is considerably greater than that for melting, but the atoms in the gas phase occupy much more space and have more microstates than in the liquid phase. Standard entropy is the absolute entropy of a substance at 1 atmosphere, and it's usually quoted with its value at 25 degrees Celsius, since most processes do occur at room temperature.
So in order for us to calculate the change in entropy of the universe from the previous equations that I showed you, we need both the change in entropy of the system and the surroundings. So we will first focus on the change of entropy of the system. It can be seen as a summation of the products considering their coefficients minus the surrounding summation of the reactants considering the coefficients. So for example, if we were to take a basic process, we'd consider the lowercase letter as the coefficients, and then we would consider the uppercase letters as just the reagents and the products. So we'll consider capital A and B as the reagents, and then capital C and D as the products. So we'll further continue it, and the change in entropy for the system can be also referred as the standard entropy of a reaction, which is stating that the difference of the standard entropies between the products and the reactions. So for example, the green being the products minus the blue being the reagents. It can be seen mathematically as the change in entropy of standard entropy of the reaction will equal the summation of the coefficients of the it would be consider the summations of the coefficients of the products, as we previously mentioned that these would be the products, so it would be, this side would be minus that of the reagents, where we consider uppercase A and uppercase B. So if we were to calculate the standard entropy of a reaction, we'd have an end product of units of J over K times mole. And if a reaction creates more in this process, creates more gas molecules represented as G. If it creates more gas molecules than it initially consumed, then the entropy would be considered positive. Or if the amount of gas molecules diminishes, then the amount of entropy would be negative. So for example, if we were to have gas molecules on the products, the reagents, and then on our product side we end up with solids, then we would consider that as a negative. But for example, if the total number of gas molecules remains the same as it was consumed, it can be the entropy can be either negative or positive. Now, since we focused on the system, the change in entropy of the systems, we will now focus on the entropy change on the surroundings. It can be symbolized as the following. In constant pressure processes, heat change will equal the entropy of the process. So the heat change will equal the entropy of the process of the surroundings, meaning that the change in entropy is proportional to the heat change. So this would symbolize proportionality, and this would be the change in entropy. So it's proportional to that of the heat. However, if there is a negative sign, there is a negative sign present. So once we take into consideration heat, the change in entropy for a specific amount of heat also will be dependent of temperature. But the negative sign is used due to the fact that in some occasions where the system itself is exothermic, it's present that the enthalpy will change of the system will be negative when the entropy of the surrounding is a positive quantity. So since we were to consideration the heat, we will also take into consideration the change in entropy for a specific amount of heat also would be dependent on the temperature of the surroundings. So once it's dependent on the temperature, we take the entire equation itself and we end up getting a rewritten reaction of itself. So it would be symbolized as the change in entropy for the surrounding systems would be the negative change in heat of the system over the temperature itself. So we've already discussed the change in entropy for the system, and we also discussed the change in entropy for the surroundings. So the calculations from the previous, you add them both together to get the total summation of the initial statement of change in entropy of the universe.
Section 17.5, Gibbs free energy. Gibbs free energy is just a more direct solution or an explanation to the second law of thermodynamics. This process can also, instead of calling it Gibson's free law, it can also be called free energy, which many scientists call it just to term it up or shorten it up a little. So basically all of this can be gotten by an equation that is G equals to H minus T times F. In this equation, T is the temperature of the equation of the system. So basically, the temperature will be given by any problem that you'll be solving for, or it could be gathered if you're doing an explanation or something. G is the units of energy, just like H and Ts are both in the energy units. So it's a very simple equation right now until it gets broken down into several steps. So by doing this, it's nothing so much different from other things or another or third thermodynamics law or anything. No, it's just a more direct solution to the second law of thermodynamics, which is just a continuation what we have learned and what we have studied about. So the change in free energy can be determined by a simple equation. It's nothing different in the first one or anything. It can be determined by the change of G. Change of G can be determined by the change in H minus temperature times the change of S. Nothing big, just normal, the same thing that we've been doing with the equation that I just gave you. You're just basically adding the change in. So remember that free energy is the amount of energy that is available to do the work. Okay, it's not an energy that appears out of nowhere or anything. It's basically the energy that you already had. So if the change in G is less than 0, then the reaction is spontaneous in the forward direction. Remember that, because these three things that I'm about to give you are very key for this. This is number one. The second one, the change of G is if the change of G is greater than 0, then the reaction is non-spontaneous. This means that the reaction is spontaneous in a way, but it's gonna go to the opposite side. Woo. And then the third one is the change in G equal to 0. This means the system is at equilibrium and there is no net change at all, which the product and the reactant equal the same thing and nothing is happening. No, the spontaneous energy is not moving forward or it's not moving to the other direction or backwards. It's just staying on the same place and nothing different. Okay, so the temperature at which a phase transition occurs in the melting point. So basically this means that the equilibrium of the system, remember the equilibrium is the change in G, will occur. This is the phase transition. So it will occur when the substance is at the melting point or at its boiling point. No more or less. It usually occurs at this time. It rarely may happen on another. The equation for this, for finding the phase transition is because we want to find this phase transition, so we're not finding equilibrium anymore. So the equation is going to turn from change of G, which is equilibrium, to finding the change of S. So in order to do this, we have to change the equation up a little bit. So from having the equation as change of G equals change of H minus the temperature times the change of S, we want to isolate the change of S by itself. So by doing that, we're gonna get rid of the equilibrium and we're gonna move the change of S to the opposite side, so to the left side. So by doing this, it's just simple as changing, simple everything. So to find the change of S is the change in H divided by the temperature. Nothing big or nothing. It's just a simple change. So the change in this equation occurs just by isolating the change of S by itself. Okay, nothing and nothing. So this is called the phase transition. It's nothing different from the Gibbs free energy or anything. It's just another thing that's tied up to everything. Remember that chemistry is tied up, many things tied up into one, where you can find everything, every kind of stuff, and all the equations equal to another one. So remember that the standard free energy of the reaction is the free energy change for a reaction when it occurs under standard state conditions, when reactants in their standard states are converted to products in their standard states. In order to find this, you need to use the equation that's lowercase a times the uppercase a plus lowercase b times uppercase b, which will give you a product of lowercase c times uppercase c plus d plus uppercase d. Nothing tough, not a big equation like a pi or anything, nothing much. This is pretty simple chemistry that's going to be going on. So remember that when all this happens, remember that the change of G is equal to 0. Whenever the change of G is equal to 0, the system is at equilibrium. Has no net change, no going forward, no going backwards or the opposite direction or nothing. Staying still. So also remember that if the change of H is negative and the change of S is negative, then the change in G will be negative only when the change of S is smaller in magnitude than the change of H. So basically, it kind of sounds complicated and everything, but in reality, it's not. It's just this long sentence that as soon as you get the hang of the equation, it will be great. So the type of condition is only met when T is smaller. So this type of condition can only be met when the temperature is smaller than the others. Okay, it's an easy step and everything. Remember to keep going, and with a little bit of practice and using these equations, everything will be easy. It's not as hard equations or anything. Nothing at all.
17.6 Free energy and chemical equilibrium. In this section, we are going to talk about how certain chemical reactions whose reactants and products are not in the same standard states
have a relationship between the change in free energy and the change in standard free energy through a process from thermodynamics. To start off, this equation or reaction derived from thermodynamics is read as the change in free energy, which equals the standard free energy change, plus R times T times LQ. In this case, your R is going to be your constant, which is going to be 8.314 joules over K times moles. Your T is going to be your absolute temperature in Kelvin, and your Q is going to be the reaction quotient. Now, your free energy change is dependent on two quantities. The first quantity is the standard free energy change, and your Q, which is the reaction quotient of the reaction taking place. At equilibrium, your free energy is going to equal 0, and then Q and K are going to be equal to each other because they are both interpreted as equilibrium constants. So in the end, 0 is going to equal to your change in standard free energy plus your multiplication between your gas constant absolute temperature in Kelvin and your reaction quotient. So your standard free energy is going to equal to the change of standard free energy, which equals your negative portion of the gas constant times the absolute temperature in Kelvin times the reaction quotient. Because as you can see, since K is equal to Q, then it is automatically going to be interpreted as the reaction quotient. Now, each reaction is going to be different and will have certain conditions which can be which will lead to certain conclusions that are identified in this table. For example, let's say your K is greater than 1, then your LK is going to be positive and your change in standard free energy is going to be negative. By having these characteristics, that automatically makes your reaction being at equilibrium, saying that the products are favored over the reactants. Now let's say that your K is less than 1, so your L and K is going to be negative and your change in standard free energy is going to be positive, meaning that at equilibrium this reaction is going to favor the reactants over the products. Now if your K equals 1, your Ln and your standard free energy are both going to equal to 0, meaning that this reaction is at equilibrium, and just as the products are favored, the reactants are going to be favored as well. So in reality, your change in free energy determines the spontaneity of the reaction's direction. Now, to have a better understanding of this concept, it is important to have a practice problem to truly understand the process of finding the constant value of a certain reaction. So in this case, we are going to calculate the constant value of this reaction right here. And the way we're going to start it off is by using the formula of your standard free energy reaction, and it's going to look something like this. Equaling the stoichiometric coefficients of your change and standard formation, free energy formation of your products minus the stoichiometric coefficient of the change in standard free energy formation of your reactants. So of course we're going to apply this equation, this formula to our reaction. So it is going to look something like this. Since we do have 2 moles of hydrogen, then we're going to write the number 2 times the change in standard free energy formation of hydrogen plus the 1 mole of O2 close off that minus 2 times the negative 237.2 kJ moles. Yeah, so after plugging those numbers in, we will get, or actually this would continue off, and here you would put 0 kg moles, kj over moles, and here as well for the oxygen, negative 237.2 kJ moles. So this would equal to 474.4 kJ over moles. Now to continue it off, we are going to use the equation used in the previous slide. So it is going to look something like this. Negative gas constant times your absolute temperature times ln Kp. And actually for our purposes, I am going to erase the first part of our equation. Or actually the whole thing. And we're gonna continue off with the formula from the previous slide. Equaling your negative gas constant times the absolute temperature of your ln Kp, which is your reaction constant. So we already found out the value for the change in standard free energy reaction, and that would be 474.4 kJ moles. Then we would multiply that times 1,000 joules in 1 kilojoule, equaling your R, your negative parentheses R, which is 8.314 J over K times moles times your absolute temperature, which would be 298 kelvins, times your L and Kp. So then eventually your Ln, after doing this whole process, you are going to want to find the value of your Ln Kp, and it would be equal to Ln Kp equaling to negative 191.5. Then you are going to want to get rid of the natural log, and by that you would have to multiply your K value divided by E times negative 191.5, which would equal to your K value being 7 times 10 to the negative 84, and this would be your final K value. And since this constant is consistent, it does not spontaneously decompose into hydrogen and oxygen gases. Since it is a large positive change of your free energy, then it is going to favor your reactants over the products at equilibrium. 17.7 Thermodynamics in living systems. In this section, we will discuss the characteristics of biochemical reactions and living systems reactions in certain conditions where they are energetically favored. So let's jump right into it. First of all, biochemical reactions have a positive free energy value. Living systems have a negative free energy value. Coupled reactions are favorable reactions that can drive another unfavorable reaction thermodynamically. And usually if a reaction has a large positive free energy value, then the reaction will not work for these purposes. And an example of this would be the extraction of zinc from ore fluoride. So it's going to be something like this. Whose free energy value is going to be equal to 198.3 kilojoules over moles. Now, in an equation that it will work, it would look like this if it had a large negative free energy value. So it would be whose free energy value is equal to negative 300.1 kilojoules over moles. Notice that your equation that will work for these purposes has to be negative, and the one that won't work will have a positive value. Now, a positive value, like I said, will not favor the formation of products, but a negative change in your free energy value will work for these purposes. In biological systems, enzymes help the variety of non-spontaneous reactions. Examples of this include food molecules, human body, and glucose for the formation of carbon dioxide and water. In living systems, glucose is broken down to help enzymes with the process of making ATP from ADP. So ATP stores free energy that is used by cells as it is needed, and ATP goes through hydrolysis to give out the ATP and phosphoric acid. And this would conclude our video for chapter 17, where we explained all of the important concepts having to do with entropy, free energy, and equilibrium.